For step 1, measure the diameter of the specimen and take the 3 reading and calculate the average of the diameter. For step 2, draw a straight line on the specimen length to measure the L and observe the effect of twisting. For steps 3, fix the both end of the specimen into the holder, mount it between the loading device and the torque measuring unit. For step 4, turn on the hand wheel clockwise to provide the applied load, switch on the measurement amplifier and set it to 0. Step number 5, rotate the wheel by choosing an increment of quarter rotation 90 degree. Following the table 1, the readout value is the applied torque. For the step number 6, repeat the step 5 by choosing an increment of quarter rotation and record the reading of the applied torque. Then we rotate the wheel until the specimen is fractured. Lastly, fill the experimental data in the table that provided and then plot the graph. Hi, my name is Alex Harrison Anthony. This is my S2, that is torsion test. So this is the result that I get. Here we can see the applied torque table, angle of twist and calculation value. And here you can see all the value that have here. This is the scale reading, revolution degree. This is amplifier reading. This is angle of twist in degree and radian. And then this is the calculation value for the shear stress and the shear strain. Now this is the result for the graph, for the steel graph. As we see here, the graph is constantly increase, and this is the graph between torque versus angle of twist, and this is the graph between shear stress versus shear strain. As you see here, also the graph is increases in the perpendicular line, in the straight line. And then this is the result for the brace. For here you can see let's say the implied torque, angle of twist and the calculation value, and this is the value that I calculated here. And then this is the brass graph, and here you can see the graph is increasing and then constant here, and then it increasing again at this point at this 4 radian or 4 degree, and at this point it's starting to increase. And then this is the graph between the shear stress and the shear strain, and before this is the graph between the torque versus angle of twist. And this is the flowing properties of the tested specimen, and here we can see the steel and the brass, and this is the diameter, the length, and this is the polar moment of inertia, and then this is the modulus of elasticity value. This is the value that we calculated. And then this is the properties and error of the tested specimen. As you can see here, they have a lot of column that is experimental value, theory and reference value, and this is the error. For the modulus of rigidity, this is the value, and then this is the Poisson ratio, and then this is the maximum shear stress, maximum torque, maximum shearing strength value, and then failure shear stress. That is 397. And this is for the brass, as we can see here. And this is for the discussion. Compare the result of this between of the experiment and the reference standard value of modulus rigidity, torsion ratio, shear stress, and shear strength. Comment any different and possible sources of error. The result between the experiment and the reference value of modulus of rigidity, torsion ratio, shear stress, and shear stress is due to the cause of thermal expansion, internal forces, and machine accuracy of leading the length and others. Describe the behavior of this material as it responds to increasing applied torque. Steel is ductile fracture if there is more torque applied at the specimen until it eventually fails to handle more torque. For the brass, it is brittle structure. The fracture will occur when it reaches the maximum capability of handling torque. For the next discussion is the Hooke's law for shearing strength and strain valid? Explain. The Hooke's law stated is the only valid for the elastic range of the material, which is the proportional limit. If it's over the Hooke's law definition, it's no longer available to define as a Hooke's law. The material will remain deformed even when the stress on the material is removed completely. And then describe the appearance of the fracture structure surface of the tested specimen and describe the mode of failure. Steel material is brittle and generally weak in a tension than a shear. When there is torsion applied, the material tends to break along a surface which is perpendicular to the direction of the force or tension. Brass material is ductile and fail and shear when applied to the torsion. The brass will break along a plane perpendicular to its longitudinal axis, and which should be able to resist more torque, a solid bar or a hollow bar of the same material. And cross-sectional area. Explain. Hollow bar is because it will resist more torque as it is light in weight. The stiffness of the hollow shaft is more than that of solid with the same weight. It also has more room to expand. For the conclusion, to determine the modulus of rigidity, maximum shearing stress, maximum shearing strain, and Poisson ratio for the tested specimen has been understood. To study the linearly elastic behavior of the tested specimen under the torsion and to obtain the relationship between the torsional load and angle of twist for a full range of strain until failure has been understood. So I think that's all for me. Thank you.